In Lesson 1.4, Continuity and One-Sided Limits, we will explore more than a working definition of continuity. We'll actually look at a formal definition of this and also look at how a function can break its continuity or become discontinuous, if you will, I suppose. Furthermore, we'll look at one-sided limits, which are very similar to the limits we learned about previously, except these occur when we only go from one direction rather than from both. We'll conclude this lesson by looking at the intermediate value theorem, a theorem that is so obvious and so common sense that it wasn't even formally codified until the 1800s. We'll talk about that, and it will make perfect sense to you as well. So, with all that being said, let's begin by looking at a formal definition of continuity. As I said, there are working definitions and formal definitions of most concepts, and continuity is no exception at all. In fact, if we want a working definition of continuity, let me go ahead and just call this working, perhaps we could say you don't lift your pencil as you draw the graph. Of course, if you're writing with a pen, you don't lift that either. But regardless, it is a graph where you just continue to draw. You never lift your pencil. Here's a continuous function. Of course, if it's a continuous graph, maybe it's not a function at all, but it's still continuous. All right? So it keeps going. You never lift your pencil. This particular graph right here is actually continuous on the interval from here to here, it appears, somewhere in that area. So if we want a formal definition of continuity, however, let's go ahead and codify this. There's three conditions that need to be met. And again, we are talking about a function. So remember that a function always passes the vertical line test. It continues moving to the right. So if we have a function, it's continuous if f of c is defined. And that is true for all values of c in the interval that we're looking at. In fact, it says here that a function f is continuous at c, so it could be any value within its domain. So clearly, the function has to be defined at that point. Furthermore, the limit of that function as x approaches c must exist. In other words, at this point c, there can't be any asymptotes, there can't be any jumps, it can't be anything like that. The limit must exist. Now, of course, the limit existing means there could be a hole there. But in number one, we said that f of c must be defined. But of course, it could be defined somewhere else that doesn't make it continuous. And so the third condition actually ties together the first two. And what we're going to say is that the limit as x approaches c of this function, which we already said exists, but we're going to say that if the function is continuous, then the limit must equal the evaluation of the function at that place. I challenge you to try to break any one of these three rules and see if you still define a continuous function. I think you'll find that you don't, but it does provide an interesting exercise. So, when we are discussing continuity, it's essentially a two-step process, and we'll see this in the next few examples here. But we want to define the domain of that function. And once we have the domain defined, then we want to determine any discontinuities. Once we do that, that is generally enough to discuss the continuity of a function. And I'll show you what I'm talking about here in example A. Example A is an example involving a step function, which hopefully you recall from pre-calculus. This particular step function we can actually call the floor or greatest integer function. It takes the value x and evaluates what is the greatest integer that is less than or equal to x, and that becomes the function's evaluation. I've also given you the graph right here so that you can take a look at this graph and see how everything works out. As a quick example, look at, let's say, f of 1.5. f of 1.5. Well, what is the greatest integer that is less than or equal to 1.5? And that would be 1. So that is where we get that point from. All right, so that's all the greatest integer function is. Now that we have an idea of that, why don't we talk about the continuity of it? The first thing that I do want to discuss is the domain of this function. And domain we often write with a double bar D for reasons steeped in math history, but we won't get into that right now. What is the domain of this function? Are there any values for which this function fails to exist? Even on the integers, you'll notice that the function clearly does exist. So there's a few different ways we can write this. The standard approach is just the parenthetical interval notation, negative infinity to positive infinity. We can write the domain that way. If you prefer, a lot of times on the BC exam, they'll write it using a inequality notation, so you can see it written like that. Or in this particular case where it could equal all real numbers, we could simply say that x is a member of the subset of real numbers. If you're not familiar with that, simply ask or look it up, and you'll see you can look it up as double bar R and see what that means. Interesting story behind that symbol. But anyway, there's our domain. However you want to say it is fine. Along that domain, however, there are some discontinuities. Notice that we're jumping from here to here, and again from here to here, and again from here to here. We keep jumping. So what we might want to say is that there are discontinuities that exist, and I'm going to write discontinuities at, I could write this in English at every integer value, and to any mathematician or anybody at your level, that will make sense at every integer value. We could say discontinuities at all x's that are the subset of integers, and integers can be written as a double bar z. Again, you can look that up, see for yourself that that is the case. So we could write it that way. Lots of different ways. As long as you explain yourself, you'll be okay. And that's how we discuss the continuity. Give the domain and tell us where it's discontinuous, and we'll infer that it is continuous everywhere else. Well, that being the case, let's take a look at a tangent function in example B and see how that one works out for us. So the graph of the function y equals tangent x, which I've shown you right here, you'll notice does have some discontinuities in it as well. So let's go ahead and do the same two steps that we did on the last problem. We'll start by talking about the domain. And in this situation, the domain looks to be all real numbers except for certain asymptotes. It looks like there's an asymptote there, and it looks like there's an asymptote here. And probably as you recall back from pre-calculus, the tangent function does have asymptotes at every pi values along the x. So how do we account for that? Well, the domain, I'm going to say, is all real numbers except I'm going to start arbitrarily at pi over 2 and then add or subtract pi n units. And of course I should define n as being a subset of all the integers. So, I didn't draw my double bar z too well there, but I think you know where I'm going with this. So our domain is all real numbers except for pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. All of these, and they're all separated by 1 pi. So that's what this second part of this exception is. Now, what kind of discontinuities exist at these? I mean, clearly we have, as far as continuity, that this is continuous on its domain. So, on its domain, we have no problems. We don't have any holes or jumps or anything like that. But we do have asymptotes outside the domain. So I'm just going to go ahead and note that. Asymptotes at, and, I could rewrite this, but I'm just going to go ahead and reference this again right here. We have asymptotes at all of those places. So there's the continuity of the tangent function. All right? Its domain is all real numbers except for those asymptotes, which exist at pi over 2, plus or minus pi times a number, an integer number in any direction. So hopefully that makes sense to you. go ahead and try C on your own before we get to it together. But I love example C, so we're going to jump into it right now. With example C, we get to a very interesting situation where we need to discuss the continuity of a piecewise function. Now, fortunately, this piecewise function is made up of two polynomials. And I will tell you right now that there are four types of functions that are continuous on their entire interval. I'll write them down here for you if you like. These are going to be called continuous on entire interval. I should say on their entire domain. So what are the four types of functions that are continuous on their entire domain? Well, we just said that polynomials are one of them. Anywhere that the polynomial is defined, it will be continuous. Secondly, we have rational functions. If you can determine the domain of the rational function, it will be continuous on that entire function. And some of you might say, but a rational function, what if there's a zero on the bottom? It won't be continuous there. I agree with you, but that would not be in its domain either. So problem solved. A rational function is continuous on its entire domain. Then we have radical functions, which we haven't dealt a whole lot with yet, but there'll be many of those to come. And last but not least are going to be our standard trig functions. So we took a look at the tangent function in our last example, but any trigonometric function, if you can find its domain, the function will be continuous over that domain. So why am I telling you this? Let's take a look at the graph of this piecewise function right here. Just looking at the graph, everything seems fine. Using our working definition, you never appear to need to pick up your pencil to draw this, but unfortunately a working definition is not going to be enough to get you points on the AP exam. So, first let's take a look at the domain of this, and I think you would agree with me that if x is less than 2, if x is greater than or equal to 2, it does seem like that the domain is x that are all real numbers. Or again, you can do your interval notation, or you can do your inequalities notation. Either way, whichever of these three you use would be acceptable. So, if the domain is all real numbers, does that automatically mean that it's continuous everywhere? Let's use our formal definition and just verify this real quick. If you remember, or even if you don't remember, look back at the box on your notes. Our formal definition said that f of c must be defined. In this case, the only real questionable point is where c is 2. So is f of 2 defined? Certainly, if you take a look at this right here, I think you would agree with me that, yes, absolutely, f of 2 is defined. So there's no problem there. Alright, so step 2, does the limit as x approaches 2 of f of x, does this exist? Well, let's take a look. The limit from the left, if I'm coming in from the left, I'll be going like this. I'll be coming around the parabola, and as I approach 2, which I will draw as a dashed red line, it seems as I approach 2 for the x that f of x is approaching 4. Okay, so from the left, I'm okay. What's going to happen when I come from the right? And you might say to yourself, well, the same thing happens. Alright, it looks like the limit, whether we come from the left or the right, the limit is going to be 4. So the limit as x approaches 2 does exist. Alright, and finally, is the limit as x approaches 2 of f of x, is that equal to f of 2 itself? Well, here we run into a sticky situation. We've already said that the limit from the left or the right exists, and I'll add it equals 4. So this right here, this limit part, we can write 4. What do I get if I evaluate this function at 2? Well, I'll be using this bottom piece of the piecewise function, and if you stick 2 in there, look what I get. I'm going to get 4. And so this does check out. So, the domain is all real numbers. By our formal definition of continuity, this function is continuous everywhere. So that's pretty cool. Let's take a look at one more example before we move into one-sided limits, which I've already alluded to on this example, but let's take a look at one more first. In example D, I've gone ahead and drawn you a graph yet again of the function represented here. F of x is this ugly rational function. I'm not going to worry about it. Here's a graph. You can look at the graph and see that clearly it's continuous, and we're good. Let's move on to the next example. Oh, wait a minute. Maybe it's not continuous. Notice that this is a rational function. So despite the way the graph might look, hopefully you can tell that if we look at the domain of this function, what would be the domain? Well, we could say that the domain is all real numbers, except for what value for x? Well, 4 would give us a 0 on the bottom. So we could write it that way. It would also be acceptable to write it this way. You can write it using inequalities, however you want to go about writing it. But certainly the value 4 is not included in the domain of this rational function. So now that we've determined as far as domains go, we could say that this function is continuous on its entire domain. After all, everywhere else but 4, everything is fine. And as we said earlier, rational functions are one of those that are continuous on their entire domain. However, let's just do a little bit of work here and just see, even though we can probably tell, let's just see what kind of discontinuity this is. I'm going to argue that if you were to factor and cancel and essentially simplify this function, you would end up with x plus 4. And certainly this is the line x plus 4 equals y. So that's all good. What is the point of all this? It tells us that our discontinuity, and I'll just write discontinuity, is removable. In other words, it is a hole, and that is at x equals 4. So even though we don't see it on the graph, there's probably a little hole right here. And your calculator might not show it either, so you have to be able to look at these things analytically and tell. Graphical is not always going to be the end-all, be-all for you. So let me present to you another situation. Let's say that this was actually a piecewise function, and it was defined this way for all x values not equal to 4. And furthermore, let's say that this function is defined as k for when x does equal 4. So I now present to you the question, for what value of k, and I'll write this out for you, for what value of k would f of x become continuous? So this is a very interesting question, and this is the kind of question that could show up on your AP exam. They love to throw these things on there. For what value of k would this piecewise function become continuous? Well, of course, following our 3 definitions of continuity, f of 4 would have to be defined, but that's no problem. We're defining it right here. When x equals 4, y will equal k, whatever that is. The limit has to exist. That means it has to be the same from the left and the right. So if we take a look at this, since our function essentially boils down to this, from the left at x equals 4, we'll get 8. From the right at x equals 4, we'll get 8. And so clearly the limit as x equals 4 would be 8. What would k have to be then? Well, k would have to equal 8. If that were the case, that would fill in this hole, and we would now have a continuous piecewise function. So just another interesting twist on this whole thing. Well, again, I've talked about limits from the left and limits from the right. Let's go ahead and take a look more at these one-sided limits and see how they can help us out. Even though we're only formalizing one-sided limits now, you've actually seen me demonstrate one-sided limits many times already. Essentially, all a one-sided limit is the limit of a function as we approach from one side or the other. Let me give you a quick example on this terrible graph I've drawn. Let's say we go like this. Oh, now that's ugly, but let's just see what happens. If I'm doing a one-sided limit as x approaches c, which I'll call this c right here, the limit of this function as x approaches c from the left, and I say from the left by putting a little negative here. If I do that, notice that I'm heading towards infinity. So this limit doesn't really exist. Although, just for the sake of brevity, I'm going to put infinity here. Alright, well, let's take a look at the limit of this function as x approaches c from the right. Well, if negative signifies left, hopefully it's fairly evident that putting a positive here will signify a limit from the right. So what would that look like? Well, I'd come here and I would go down forever and ever and ever. So although the limit doesn't really exist, I'll say that the limit tends to negative infinity. Does this function have a limit at c? No, it doesn't. And that's because its two one-sided limits are different. Alright, so that's the idea of one-sided limits. Coming from the left, seeing where it goes. Coming from the right, seeing where it goes. That's the whole idea. However, I'm going to argue you can still do direct substitution, and that's still the best way to do it. Take a look at this problem here. This is nasty. This is ugly. I want to find the limit of all this ridiculousness as delta x approaches 0 from the left. It's small, but there is a little negative there. So the limit of all this crap as delta x approaches 0 from the left. Of course, if you want to do direct substitution, absolutely go ahead, see what happens. I can already tell I'm going to have a 0 on the bottom, so that's no good. I'm going to encourage you to pause the video here and do some algebraic manipulation to see what you end up with. Come back when you're ready. However, I'm going to begin by skipping straight to the jugular here. And I'm about to give it away, so go ahead and pause, simplify it out. And the opportunity has been had. So if you do simplify this, what you are going to get, if you do it correctly, is 2x plus delta x plus 1. And at this stage, you can plug 0 in for delta x. That should not be an issue for you here. In fact, if you do plug 0 in for delta x, what you'll get is 2x plus 1. And that, in fact, is the limit of all this nastiness as delta x approaches 0 from the left. So, here's a conceptual question for you. What would happen if I wanted to know the limit of all this nastiness right here, the limit of all this, as delta x approached 0 from the right? What would happen then? Well, again, you can carry out all your algebraic simplification. At the end, you could plug your 0 into delta x, and you'll still get the same thing. What that tells me is that the limit from the left equals the limit from the right, and so it probably is continuous at that place, assuming that f of 0 equals whatever's going on here. Anyway, we'll get more to that later involving derivatives and all that good stuff. What I want to do now is take a look at example f, which involves another function that can be simplified, broken down, and toyed with that way. Let's take a look. On example f, we have a rational type of function, but one that can very simply be broken down and simplified. So we're trying to find the limit of this as x approaches 4 from the right, from the positive side, which is why there's a plus sign there with the 4. So if we take a look at this, if you're not quite sure how to simplify it, it might help you if you look at it in exponential terms. So this is x minus 4 to the 1/2 over x minus 4 to the 1. And now if we use our simple algebra 2 exponent rules, what we're really trying to find is the limit as x approaches 4 from the right. Let's see, if we simplify that, we'll have 1 over the square root of x minus 4. Now, what's going to happen here as we approach 4 from the right? You could just graph this in your calculator, and I'll show you a graph of this in just a moment. But what I want you to think is, as I move closer and closer to 4, is this thing getting bigger, smaller? Is it getting closer to something? And in fact, what I've done is I've gone ahead and created a chart for you right there. So you can go ahead and take a look at that. And when x is 4.5, you see what f of x is. But as x gets closer and closer and closer to 4, it keeps inching closer to 4 from the positive side, look what happens to f of x. Keeps getting bigger and bigger and bigger without bound. It doesn't seem to be limiting to any value. And so what we can say about this, the limit as x approaches 4 from the right side of 1 over square root of x minus 4, we can say that this limit does not exist, as it tends to increase without bound. And I'm actually going to write that here, increase without bound. Now, some mathematicians and some people will tell you that what that means is that the limit, as x approaches 4 from the right, of this function, they would say that this means that the limit is actually equal to infinity. I'm going to argue it can't actually equal infinity because infinity is not a number, but at least writing that tells us that it is tending to grow and grow and grow. One last question for you before I show you the graph. What would the limit of this function be as x approaches 4 from the left? Think about that for a moment. Go back to our simplified function, which is this guy right here. And what would happen if we approach 4 from the left side? Start with 3. What would happen if I stick 3 in here? It fails to exist. How about 3.5? How about 3.9? All of these cause this function to fail to exist. So now let me go ahead and show you the graph right up there. And sure enough, as we approach it from the right side, it looks like the function's going up to infinity, and we can't approach it from the left side. That just really is not possible. So there you go with one-sided limits. I want to take a look at one more example involving examples G, H, and I, which we'll do all together at once. And if you take a look at those, you'll see why. So let's explore those now. For our final 3 examples dealing with one-sided limits, we're going to revisit the step function, the greatest integer or floor function that we played with in example A here of these notes. So again, I've drawn the graph for you. You see it right there. Also, I've drawn a vertical blue line at x equals 2 because that's where we're going to be looking at the limit of this function. In example G, in fact, we're looking at the limit as x approaches 2 from the right side. There's the plus sign there, from the right. And so if we do that, that's going to put us on this step going towards 2 from the right. What is the y value for this? Hopefully you can see clearly it's 2. So if we move to example H, we're going to do the same limit, but this time we're going to approach 2 from the left, which is actually going to put us on this step. And what's the limit of that? Well, it looks like y is equal to 1. And so overall, what is the limit as x approaches 2 of this step function? Remember that in order for a limit to exist, its left limit and right limit need to be equal. Here, they are not. And in fact, what I'm going to say is that the limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right. And for that reason, this limit does not exist. It's not that it doesn't exist and we could say, oh, but it tends to go to infinity or it tends to go down without bound. This limit has no chance of even being described by tends to or anything like that. The limits are different from both sides, and so the limit overall just doesn't exist. Now, all this being done, I do want to show you the intermediate value theorem, something that doesn't really seem to apply here, but is extremely important, very commonsensical, and once I explain it to you, you'll wonder why you had to wait till calculus to learn this theorem. The intermediate value theorem, a theorem that is simply so obvious that you're going to wonder why you didn't come up with this yourself. Let me explain it. We have a function that we're going to call f, and f is a continuous function of some sort on some interval. Now, I'm going to call that interval from a to b, and we'll put it here and here. So here's the interval a to b. I don't care what f does outside the interval. It can have asymptotes, non-removable, removable discontinuities, but on the interval from a to b, f is continuous. Now, furthermore, we know that right here, this y value is f of a. And furthermore, this y value right here, which I'm going to drag across, is f of b. So not only do I know where this interval begins and ends, that's a and b, but I also know the y values at its endpoints. No big deal so far. Let me go ahead and introduce a new value that I'm going to call k. and I'm going to put k right here. So long as k is between f of a and f of b, so long as k is somewhere in between there, then the intermediate value theorem guarantees me that there is a value c such that f of c equals k. In other words, if I know the y values at the beginning and end of an interval, and the function is continuous, it must pass through every y value between f of a and f of b. That's all it's saying. K is some other y value, and the theorem just says there is an x value that when I evaluate the function there, I get that y value. It's a little confusing, but hopefully this picture helps. Let me go ahead and throw up some text for you that you can copy down. You may need to pause the video, but notice it says that if f is continuous on a to b. That's very important. That condition must be met. And it tells us that k must be some value between f of a and f of b. That condition must be met. And if both of those conditions are met, then there does exist some number c such that f of c equals k. It's a beautiful theorem. It's simple. Let's take a look at a couple examples where you would actually use this. So, in this example, we're first going to verify that the IVT, or intermediate value theorem, actually applies to this function on its interval. And then we'll go beyond the bounds of the IVT and try to find the actual value of c that the IVT guarantees us. What do I mean by the value of c that's guaranteed by us? The IVT is simply an existence theorem. It tells us, is there a c such that f of c equals k? Doesn't tell us how to find it, doesn't tell us where it is, doesn't tell us anything. Just, is there a value of c such that that happens? So really, if we meet both of the conditions for the IVT, then all we can say is, yes, the IVT guarantees that there is at least one value of c for that. Let me go ahead here, work this out, and show you what I'm talking about. Before we can do anything here, we need to check our two conditions for the intermediate value theorem. First off, is f of x continuous on the interval from 0 to 5 inclusive? And of course, f of x is a polynomial. A polynomial is continuous on its entire domain. And so the first condition is met. The second condition is we need to check f of 0 and f of 5 to see if our value of k is actually between those two y values. Well, I did this beforehand, and f of 0 is 8, f of 5 is 3. Well, our k is 0. And so at this point, is our k between f of 0 and f of 5? In this situation, clearly, it's not. And so the second condition fails, and all we can say then is that the IVT, or the intermediate value theorem, does not apply. And again, why does the IVT not apply? Because k is not between the two y values. Alright, so I'm going to propose a similar problem to you. We're going to use the same function, f of x equals x squared minus 6x plus 8. But this time, we're going to use it on the interval 0 to 3. And all I want to know is there a c such that f of c equals 0? Well, go ahead and try this problem out on your own. I will tell you that the answer is yes. I will tell you that. The answer is yes. And beyond that, go ahead and try it and see what you end up with. Remember, the IVT is only going to tell you, is there such a value? And then it's up to you to go ahead and try to find what those values are. So pause the video, give that a quick shot, and I'll meet you back when we get to example J. And our last example is pretty much just a rehash of our previous example, where we're just going to check some conditions and see if the IVT applies to this. So let's go ahead and begin. We do have this rational function, and we're looking on this kind of nasty interval. But is f of x continuous on that interval? Now we need to be careful here. You might say to yourself, well, f of x is not continuous because something happens at x equals 1. However, I would argue that it doesn't matter what happens when x equals 1 because our interval starts at 5 halves. Is f of x continuous on this interval? Yes, it is. So we passed the first condition. Now what we need to do is check the values of f of 5 halves and f of 4. Feel free to go ahead and give that a shot. That's a fun little exercise in algebra, I suppose, or arithmetic if you like. I will tell you that f of 5 halves is in fact 35 sixths, and f of 4 is actually 20 thirds. Those are pretty nasty fractions, but remember that our k value is 6. Is 6 actually between these two? Well, 6 is higher than this, so I could do this, and 6 is lower than this, and so certainly 6 is captured between those two y values. What does this mean to us? It means that the IVT does apply, and that's good news. Now, the next step of this problem is to find the value of c guaranteed by the IVT. In other words, what value of c, for which value of c would I get f of c equals 6? Well, that shouldn't be too bad. F of c, if you plug c into this, is simply going to be c squared plus c all over c minus 1. That should equal 6. And from there, all you need to do is a little bit of math. If you want to pause the video, work it out, and see what you get, I will tell you right now, you will get 2 answers, but only one of them is correct. Interesting. So pause the video, give it a quick shot, come on back when you're ready, and I assume you've done it now. If so, what you've gotten here is that c can either equal 3 or c might equal 2. So at first glance you would say, well, both of those values are correct. I found 2 answers. But remember, the interval that we're looking on goes from 5 halves to 4, and 2 is not in that interval. And so the IVT guaranteed me a value for which f of c would give me 6. I just found out algebraically that that value is in fact 3. So there we go. The IVT works together with Algebra 2 and Pre-Calculus to give you very common sense type results. You might argue, why don't we just go ahead and find the answer and not worry about the IVT at all? But trust me, the AP test writers will expect that from you and will write their test questions so that you cannot actually work it out algebraically. And then you have to revert back to your knowledge of the intermediate value theorem. So, in this lesson, we've run through continuity. We found a formal definition of continuity, in fact. From that formal definition, we went ahead and took a look at one-sided limits, limits from the left and limits from the right, and sometimes they meet and the limit exists, and sometimes they don't. And then we have other things happening. From there, we went ahead and looked at the intermediate value theorem, and so we have covered a lot in this lesson. But keep your notes handy, look over them as you work through your homework, and good luck.